Good morning, good afternoon, good evening, Fennec Friars. Today we are going to be deriving the physics kinematic equations. My name is Ethan Wagner. Let's begin. To begin, we will be taking A equals dv dt. First step to turning this into a kinematics equation is multiply both sides by dt. We are then left with A dt equals dv. From here, we will simply take the integral of both sides, the left side with respect to t, the right side with respect to v. So the integral from 0 to t of a dt is equal to the integral from v naught to v final of dv. This will get you a t from time t equals t to time t equals 0 equals v from v final to v initial. Continuing onward, we have a t minus a times 0 equals v minus v initial. A times 0 is simply 0, and by adding v naught to both sides, we have the equation v equals v naught plus at, the first of the three kinematics equations we will be deriving today. Next, we are going to begin with v equals dx dt. Our first step here, however, will not be to multiply dt over. Instead, we are going to take our previous solution, v equals v naught plus at, and substitute that in for v equals dx dt. So now we have v naught plus at equals dx dt. Do not be frightened by this. We'll simply multiply dt over, and we are left with v naught plus at, all dt'd, equals dx. Now we are going to take our integrals, left side with respect to t and the right side with respect to dx. From time t equals 0 to time t equals t, v naught plus at dt equals integral from x initial to x final dx. The left side of this will be v naught t plus not att, but a 1/2 at squared. Do not forget your power rule. From t to 0 equals x from x final to x initial. Plugging in our values, v naught t plus 1/2 at squared. And if we continue plugging in the zeros and subtracting those, we realize v naught times t equals 0, and 1/2 at, v naught times 0 equals 0, and 1/2 times a times 0 is also 0. So that entire subtraction piece is simply 0. So we don't have to do it, because subtracting by 0 does nothing. On our right side, we have x minus x final minus x initial. For those of you who know, x minus x final is the definition of delta x. And so our equation becomes delta x equals v naught t plus 1/2 at squared, our second of three kinematics equations. Lastly, for our third kinematics equation, we are going to set up a bit of a word soup. Pardon me, a word soup fraction. We have dv dx equals dv dt times dt dx. What we are saying here is that dv dx equals dv dx times dt dt. It works. Now, to solve dt dx, if we look at v equals dx dt, if we multiply both sides by dt, we have v dt equals dx. If we divide by dx, we have v dt over dx equals 1, and divide by v, dt dx equals 1 over v. And so that is what we are going to be substituting into our dx, or dt dx. And if you remember from our first equation, dv dt equals a. And so dv dx will now be equal to a times 1 over v. We're going to multiply both sides by v, and that will give us v dv over dx equals a. Multiply again, both sides by dx, v dv equals a dx. Not so hard now, is it? Taking our integrals, we have integral with respect to v of v initial to v final of v dv equals integral from x initial to x final of a dx. Our left side, 1/2 v squared. Don't forget your power rule. From v to v naught equals ax from x final to x initial. Simplifying this, 1/2 v squared minus 1/2 v naught squared equals ax final minus ax initial. Looking at this right side, a times x final minus a times x initial is the same thing as a times x final minus x initial. And as you remember from our previous problem, that is delta x. And so this side becomes a delta x. Then we're going to add 1/2 v naught t to both sides. And so 1/2 v squared equals 1/2 v naught squared plus our a delta x. Now we're going to do one last step and multiply all these terms by 2, and we will be left with v squared equals v naught squared plus 2a delta x, our third and final kinematics equation. Thank you for joining me, and enjoy the rest of your day.